Custom eval scripts break down fast. Inspect AI gives you tasks, solvers, and scorers so the harness can grow with the system. You'll learn how the pieces fit into a workflow that collects tasks and evaluates competing prompts with repeatable runs. I'm Professor Pine, teaching AI engineering and LLM systems with simple Python. Evaluations feel simple until they do not. You start with a few handwritten examples and a couple of prompts. Then you add a new prompt style, then a new model. Suddenly, you've got dozens of ad hoc scripts and no reliable way to repeat an experiment. Inspect AI eval harness in Python solves that exact workflow headache. Register tasks, attach solvers that generate completions, and plug in scorers that judge correctness. The point is stable, auditable comparisons across prompt variants and model endpoints. At its core, this is about reproducibility and fast iteration. Picture a 10-sample geography quiz. You want to try 3 prompt styles across 2 models. The win condition is simple. Queue every combination, run them without rewriting the tasks, and get a clear leaderboard. Inspect does this by treating tasks, solvers, and scorers as first-class objects, so experiments grow cleanly instead of turning into brittle glue. It's handy for small demos and scales up later. Here's the workflow in plain terms. Define the task once and bind a dataset plus a grading rule. Then add solvers that call different models or prompt elicitors. Sweep prompt variants across model endpoints and collect scores. The harness also logs metadata like versions and style names, so you can trace which elicitation caused a change. The strength is repeatability and clarity. The trade-off is a small initial setup cost, which pays off when you run many combinations. We'll build a compact example. Register a geography task, create multiple prompt variants, fan those prompts to model IDs, and aggregate a simple accuracy table. You'll see how to keep the dataset fixed while swapping prompts, and how Inspect logs the choices so you can trace back which prompt caused a change. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now, we will register a minimal task so the harness can reference it without reworking files. This snippet sets up a tiny Inspect AI task that pairs a MemoryDataset with the match scorer. The big question here is how to wrap your existing geography prompts in Inspect without rewriting everything each time experiments expand. By registering capitals with the @task decorator, Inspect captures both the in-memory samples and the grading strategy, so you can reuse them from Python or the CLI. The print shows samples equals 2, confirming the toy dataset is registered and ready for repeatable reuse. Next, we make that task configurable, so we can flip prompt styles without copying files. This example parameterizes the Inspect AI task, so you can flip prompt styles without cloning files. Engineers worry about reproducibility, so capitals run adds a style switch while explicitly binding the generate solver and a semantic version string. Inspect logs preserve those details, making it obvious which elicitation you shipped when scores change later. The console shows default task, capitals, concise, verifying the default configuration registers under a stable namespaced task name. With a parametrized runner, you can assemble multiple prompt texts. The next step is to register those variants in one place for easy toggles. This code builds a prompt registry so Inspect AI can juggle multiple prompt variants in one harness. A common question is which rewrites deserve another model sweep, so I stash capitals run style equals style outputs in the prompt variants dict for quick toggling. Capturing base dataset from the concise variant keeps every solver pointed at the same samples, protecting against accidental drift when iterations pile up. Seeing variants prepared equals capitals concise, capitals guided, capitals rationale, tells us all three prompt names are ready for queued comparisons. Once you have prompt variants, you need to decide how to pair them with models. The next snippet fans those combinations into a run plan. This snippet composes a cross-product matrix that pairs inspect AI tasks with candidate model endpoints. The operational decision is how to fan out experiments, so the product call expands model IDs against the two prompt styles you actually plan to scrutinize tonight. Run matrix now captures the exact task objects alongside their model IDs, meaning you can feed it straight into a eval set or hand it to a scheduler. The line runs planned equals 4 confirms every intended combination is queued before you spend time or credits. After runs finish, you want a quick sanity check before opening detailed viewers. The final snippet computes that leaderboard. This example distills recorded inspect AI runs into a quick accuracy leaderboard for prompt and model combos. After a batch finishes, you often just have raw completions. So completed runs stores outputs per model style, while targets pulls the shared gold answers from base dataset. Looping through the dictionary computes rounded accuracies and updates best, giving you a snappy sanity check before diving into full inspect log viewers. Best combo, GPT-OS20B. Concise 1.0 tells us the concise prompt on GPT-OS20B hit perfect accuracy on this toy set. In a real project, this toy maps directly to a controlled A/B test. Replace the memory dataset with your annotated corpus and swap the model IDs for production endpoints. The harnessed task names and versioned runs make it easy to trace regressions as you change prompts or models. Recap. A quick pattern. Register tasks, solvers, and scorers, so experiments are repeatable and traceable. Use it whenever you plan to sweep prompts or models and need auditable comparisons. The upfront design step is small, but it pays off once you run many combinations. Next step, scale this exact approach to a larger corpus and add timing and accuracy checks so you can measure trade-offs between speed and quality. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.